This is Malbork Castle, 700 years old and still perfect. Both are brick, both faced weather and time, only one is dying. The question haunted me: why does ancient craftsmanship outlast modern engineering by centuries? The answer isn't what you expect. It's not a lost ingredient, not a secret recipe. It's something far more profound and far more damning about everything we build today. Medieval masons understood a truth that modern construction has completely abandoned. Buildings aren't static objects. They're living systems. They need to breathe. They need to flex. They need to heal themselves. The proof is everywhere. 700-year-old castles stand strong, while 20-year-old buildings crumble. Today we're going to expose the fatal mistake in modern brick construction. We'll reveal why Portland cement is slowly destroying your walls, and we'll uncover the self-healing medieval technique that created buildings designed to last 1,000 years. By the end of this video, you won't just see bricks and mortar, you'll see either a death sentence or a masterpiece, depending on when it was built. Before we dive in, drop a comment. What's the oldest brick building you've ever seen in person? Let's see who's encountered true craftsmanship. Part 1. The Modern Brick Nightmare. To understand the genius of the past, we first have to confront the mistakes of the present. Why does a modern brick wall, built with 21st century technology, start to fail so quickly? The problem isn't one single thing, but a catastrophic failure of the entire system, a system built on flawed assumptions. And it all starts with the mortar. For the last century, construction has been dominated by one binder, Portland cement. Patented in 1824 and widely adopted by the mid-20th century, it was a miracle of the Industrial Revolution. It sets fast, it gets incredibly hard, and it's cheap to mass produce. From an economic standpoint, the advantages were obvious. It allowed for faster construction, which meant lower labor costs and quicker profits. The new rule became stronger is better, and Portland cement was king. But this strength is a trap. Modern mortar glues bricks into a single, monolithic panel. This rigid slab is strong, but it has zero flexibility. Buildings, however, are not static. They move, they settle, they expand in the summer heat and shrink in the winter cold. A medieval wall was designed to accommodate this movement. A modern wall is designed to resist it, and in that resistance, it plants the seeds of its own destruction. When a modern rigid wall tries to move, stress builds up until something has to give. And here's the critical failure. The Portland cement mortar is often harder and stronger than the brick itself, so it's the brick that breaks. This leads to cracking and most visibly to something called spalling, when the face of the brick literally flakes or blows off, exposing its softer interior. You've seen it on countless buildings, a diseased look that signals a wall in deep distress. And now we get to the fatal flaw of modern masonry, its relationship with water. The old masons knew that water will always get into a wall. Their system was designed to manage it. Modern construction, in its arrogance, tries to create an impenetrable barrier. The Portland cement mortar is not only hard, but also highly waterproof or impermeable. This sounds good, right? But the barrier is never perfect. Water finds a way in through tiny cracks or failed sealant joints. Once inside, that water is trapped. The impermeable mortar that was supposed to keep water out now prevents it from getting out. The wall cannot breathe. So the trapped moisture has only one escape route, through the face of the brick itself. As the water evaporates, it carries soluble salts that are naturally present in the brick, and more importantly, in the high-alkali Portland cement. When the water reaches the surface, it leaves these salts behind as a white, powdery stain called efflorescence. While sometimes just ugly, efflorescence is a sign of a deeper sickness. It tells you the wall is saturated and can't dry out. Even worse is when those salts crystallize just under the surface of the brick, a condition called cryptofluorescence. As the salt crystals grow, they exert immense pressure, blowing the face of the brick apart from the inside. The very material designed to create a strong waterproof wall is actually creating a pressure cooker for its own destruction. Here's something shocking. The International Association of Certified Home Inspectors found that this osmotic pressure from crystallizing salts can reach 2,000 to 3,000 psi, exceeding the structural strength of most concrete. The brick literally explodes from internal pressure. But there's another problem engineers call wicking. A brick wall with impermeable Portland cement mortar can absorb moisture through capillary action over incredibly long distances, up to 6 miles through microscopic pores. The water rises through the wall like a tree transporting water from roots to leaves. But when this moisture reaches the top, it has nowhere to go. The impermeable mortar traps it, so it accumulates, and accumulates, and accumulates, and accumulates. Eventually, the hydrostatic pressure, the physical pressure of trapped water, can exceed 3,000 psi. The brick literally explodes from the inside out. Medieval lime mortar avoided this completely because it allowed water to evaporate uniformly throughout the wall. No buildup, no pressure, no explosion. The bricks themselves are also part of the problem. Modern bricks are marvels of industrial efficiency. They are machine extruded into perfect shapes and baked at extremely high uniform temperatures in massive tunnel kilns, often above 1100 degrees Celsius. This process creates a brick that is very hard, dense, and less porous. It's a homogeneous, brittle unit. Like the mortar, there's no give. And here's the cruel irony. When bricks are fired uniformly above 1100 degrees Celsius, they become vitrified, almost like glass. This makes them dense and impermeable, but also extremely vulnerable to thermal shock. When temperature changes rapidly, the vitrified brick cracks like glass thrown into a fire. A medieval brick fired at lower and varied temperatures maintained its porous crystalline structure. When temperature changed, the brick could expand and contract without cracking. Our superior technology created bricks that are destroyed by the simple freeze-thaw cycle of winter. So what we have is a system in conflict with itself. Hard, brittle bricks are glued together with an even harder, impermeable mortar, forming a rigid, unbreathing panel. This is often just a thin facade, a single layer attached to a backing structure, a far cry from the thick, solid walls of the past. It's a system designed for speed and profit. Durability, it seems, was left out of the equation. We've engineered a perfect storm of self-destruction, all in the name of progress. A 2006 study of 1970s buildings in Istanbul found that after just 30 years, 42% showed severe spalling. Meanwhile, Byzantine structures in the same city, built 1500 years ago with medieval techniques, still solid. Part 2. The Lost Art of the Medieval Brick. Stepping into the world of a medieval builder is like entering a different reality. They didn't have scientific journals or computer models. They had something more valuable, generations of wisdom passed down from master to apprentice. They understood their materials not as inert products, but as partners. The longevity of their work is no accident. It's the direct result of a philosophy that worked in harmony with nature. Let's start with the brick itself. Unlike today's factory products, a medieval brick was a creature of its environment. The clay was dug locally, often right from the building site. This meant every region had its own unique bricks, but the real magic happened before the firing. The clay was often left to weather for an entire winter. This slow process, known as frost action, was crucial. Water in the clay would freeze and expand, breaking down the dense clumps on a microscopic level, naturally refining the clay and making it more workable. Modern high-speed production simply can't replicate this. When ready, the clay was mixed with water and maybe some sand, then shaped by hand in wooden molds. This process was naturally imperfect. Each brick was slightly different. In our modern world, this would be a defect. For the medieval mason, it was a reality to be worked with. These irregularities were accommodated by thick, forgiving mortar joints, creating a wall that was a mosaic of unique pieces, not a rigid grid of identical units. Next was the firing. Instead of massive industrial kilns with uniform temperatures, medieval bricks were often fired in simple structures called clamps, basically a massive, carefully built pile of the unfired bricks themselves, with tunnels at the base for fuel. The firing was slow, and the heat was anything but uniform. The kiln temperature rose gradually, igniting fuel in the clay at about 800 degrees Celsius and peaking at an average of 1200 to 1400 degrees Celsius at the center. Bricks near the fire baked hard, while those on the outer edges were fired at much lower temperatures, sometimes as low as 600 degrees Celsius. This resulted in a useful variety from a single firing. The hard-fired clinkers were used for the outer faces of walls, while the softer under-fired bricks were more porous and used for the internal parts of the wall, protected from the weather. This process meant the typical medieval brick was more porous than its modern counterpart. A porous brick can absorb water, but it can also release it easily. It acts like a sponge, drawing moisture in and then letting it evaporate. It breathes. A modern dense, high-fired brick has low porosity. It resists water at first, but once water gets in, it's very difficult for it to get out. The medieval brick was part of a system designed for moisture management. The modern brick is part of a system designed for moisture resistance, a battle it's destined to lose. Finally, there was the construction itself. Medieval builders created thick solid walls with multiple layers. While a modern wall is often a single withe veneer, a medieval wall could be 2, 3 or more withes thick. They used sophisticated bonding patterns, like the English or Flemish bond, where bricks were laid both lengthwise and end-on. These patterns weren't just decorative. The header bricks passed through the wall, physically tying the withes together into a single massive structural unit. This created a wall with immense stability, a system of incredible integrity built by craftsmen who understood the materials in their hands. The English bond is considered the strongest of all bonding patterns because it alternates complete courses of headers and stretches, ensuring maximum structural integrity. Every header course ties the entire thickness of the wall together. It's engineering disguised as craftsmanship. Part 3. The forgotten genius of lime mortar. If the brick was the body of the ancient wall, lime mortar was its lifeblood. The switch from soft, breathable lime mortar to hard, rigid Portland cement is arguably the single biggest reason for the decline in durability of modern masonry. To understand medieval construction, you have to understand lime. For millennia, mortar was made from lime. The process starts with limestone, calcium carbonate, which is burned in a kiln. This drives off carbon dioxide and creates quicklime. To make it usable, this quicklime is slaked by adding water, which produces a soft, buttery paste called lime putty. This is then mixed with sand to create the mortar. So far, just chemistry. But here is where the genius begins. When this lime mortar is in a wall, exposed to the air, it begins a slow process called carbonation. Over weeks, months, and even years, the mortar gradually absorbs carbon dioxide from the atmosphere, slowly turning back into limestone, the very same rock it started as. This is the lime cycle, a perfect, elegant loop. Here's something medieval builders knew that we've forgotten. Lime putty improves with age. Medieval craftsmen frequently left their lime putty maturing in covered pits for months or even years before using it. During this aging period, the calcium hydroxide continued reacting with water and small amounts of carbon dioxide, forming an incredibly fine colloidal structure. The older the putty, the smoother and more workable it became, and the stronger the final mortar would be. Some historical records mention lime putty that had been aged for 5, 10, or even 20 years. Modern builders, they mix and use the same day. We traded quality for speed and called it efficiency. The mortar this creates is fundamentally different from modern cement. First, it is soft. Old bricks were often quite soft, so a soft lime mortar was a perfect companion. It acts as a forgiving cushion that can flex with the building's natural movements. Hard Portland cement, which can be many times stronger than the bricks, creates stress that leads to cracking. And here's the genius medieval masons understood. The mortar was designed to be sacrificial. It was deliberately made weaker than the bricks. When the wall moved, when moisture attacked, when time took its toll, it was the mortar that yielded first, not the valuable bricks. And here's the brilliance. Replacing mortar between bricks is simple and cheap. Replacing broken bricks, expensive and structurally dangerous. Modern Portland cement mortar is stronger than the brick. So when something has to break, it's the brick, the most expensive and difficult component to replace. We created a system where the sacrificial element is in the wrong place. It's like building a chain where the strongest link is the one you need to break first. Second, and most importantly, lime mortar is porous and breathable. It has a high vapor permeability, meaning water vapor can pass through it easily. This is the absolute key to the medieval wall's ability to manage moisture. Water doesn't get trapped. Instead, it's wickered through the porous network of the bricks and mortar joints to the surface, where it safely evaporates. The wall is in a constant state of breathing. Portland cement shuts this process down, trapping moisture and leading to decay. But the most astonishing property of lime mortar is its ability to self-heal. This isn't a myth. It's a well-documented chemical process. Over time, tiny micro-cracks form in the mortar. When rainwater penetrates these cracks, it dissolves some of the free calcium hydroxide still present in the mortar. This calcium-rich water is carried deeper into the cracks. As the water sits there, it slowly absorbs carbon dioxide from the air, triggering the carbonation process all over again. New calcium carbonate crystals form, literally knitting the crack back together from the inside out. The self-healing isn't instantaneous. It can take weeks or months, but it happens continuously, silently, invisibly. While you sleep, while the seasons change, while the years pass, the mortar is constantly repairing itself. It's like having an army of microscopic workers doing maintenance 24/7 at no cost, with no supervision for centuries. Modern cement, once cracked, it stays cracked forever. If this blew your mind like it did mine when I first learned it, hit that like button. Subscribe so you don't miss how our ancestors solved problems we're still struggling with today. But the medieval builders took this even further. They inherited a secret from the Romans that made their lime mortar even stronger: crushed brick dust, called coquipesto by the Romans, and horasan in Turkey. This finely ground brick powder, mixed into lime mortar, created what's called a pozzolanic reaction. The brick dust contained silica and alumina that reacted with the calcium hydroxide in the lime to form calcium silicate hydrates, the same compounds that give modern concrete its strength. But unlike Portland cement, this compound maintained the breathability of lime while gaining hydraulic properties. It could even harden underwater. The Hagia Sophia in Istanbul, built in 537 AD, used lime mortar with crushed brick in its massive domes. A study published in the Journal of Archaeological Method and Theory confirmed that these Byzantine brick-lime mortars had considerable mechanical strength and longevity due to amorphous hydraulic formations at the crushed brick and lime interfaces. 15 centuries later, after earthquakes, wars and time, it still stands. The cathedral has undergone large static deformations, yet the mortar's very long curing period and energy absorption properties prevented catastrophic failure. The entire system, porous bricks and soft, breathable, self-healing lime mortar, formed a perfectly integrated whole. It was a system designed with humility, one that acknowledged the power of nature and sought to coexist with it rather than conquer it. Part 4. Why we abandoned wisdom. If medieval methods were so durable, why did we stop using them? The answer has nothing to do with performance. It is a story of economics, industrialization, and a shift in what society values. It is the story of how we traded longevity for speed. The decline of lime began in the 19th century, a period of explosive urban growth. Traditional building methods, reliant on craftsmanship and slow-setting materials, couldn't keep up. The lime carbonation process, for all its benefits, is slow. It can take months or years for a deep mortar joint to fully cure. The Industrial Revolution demanded speed. Time was money. In 1824, an English mason named Joseph Apstein patented Portland cement. Its advantages were perfectly tailored to the new industrial age. It set in hours and achieved very high strength quickly. This meant buildings could rise faster and schedules could be shortened. Furthermore, it could be mass-produced cheaply and consistently. Initially, Portland cement was just added to lime mortar to speed up the set time. But as the century wore on and the mantra of stronger, faster, cheaper took hold, the proportion of cement grew. By the mid-20th century, traditional lime mortar had been almost entirely replaced in new construction. An entire generation of architects and masons grew up knowing nothing else. The ancient knowledge of lime faded into obscurity. This shift was matched by changes in the bricks themselves. The demand for speed and uniformity led to the machine-made, high-temperature-fired bricks we know today. Their hard, precise forms were suited to thin, strong cement joints. The slow-setting lime mortar was a drag on profit, so it was replaced by a system of hard, brittle components that could be assembled quickly. The consequences weren't immediately obvious. The new buildings seemed strong, but they were aging in a way their ancestors never did. They were brittle. They couldn't breathe, flex, or heal. The economic incentives of modern construction, prioritizing low upfront costs over long-term performance, ensured this flawed system became the global standard. We became incredibly good at building things that wouldn't last, and we convinced ourselves this was progress. The crumbling brick of a 20-year-old building and the enduring majesty of a 700-year-old cathedral tell a different story. What we lost, and what we can regain. So here we are, surrounded by buildings that are prematurely aging, crumbling under the weight of our own supposed ingenuity. We have mastered the science of creating materials that are harder and stronger than ever before, and in doing so we have built a world that is shockingly fragile. The paradox is this: the secret to the 1,000-year lifespan of medieval brickwork was its weakness. It was the softness of the lime mortar that allowed walls to flex. It was the porosity of the bricks that allowed them to breathe. It was the slow chemistry of lime that allowed it to heal its own wounds. It was a holistic system where every part worked in harmony. What we build today is the antithesis of this. We use isolated components locked in a dysfunctional battle with each other and the environment. We've traded the wisdom of a flexible, breathable system for the illusion of a strong, impenetrable one. We've traded durability for short-term profit. And there's one final irony. Medieval buildings don't just last longer, they create better spaces to live in. The thick, breathable walls naturally regulate humidity and temperature, creating what architects call a microclimate. In summer, the walls absorb moisture and keep interiors cool. In winter, they release this moisture gradually, maintaining comfortable air. Modern buildings, with their thin, impermeable walls, they fight nature with air conditioning and dehumidifiers, consuming energy constantly to do what medieval walls did naturally, for free. We didn't just build buildings that last less. We built buildings that cost more to keep comfortable every single day of their short lives. But the story doesn't have to end here. The secrets of the medieval masons are not lost. They are being rediscovered. A quiet revolution is beginning as architects and engineers look to these ancient principles for sustainable solutions. Modern science is now validating this ancient wisdom, confirming the self-healing properties of lime and the superior moisture management of breathable walls. There's a growing recognition that the most advanced building isn't the one with the newest materials, but the one designed to last the longest with the least intervention. The majestic brick castles and cathedrals that still stand are more than just historical curiosities. They are a message to us from the past. They are a physical testament to a philosophy of patience, harmony, and respect for materials. They prove it is possible to build for the ages. The question now is, will we listen? And what about you? Have you seen a relatively new brick building that's already falling apart? Or do you know of an ancient one that still looks incredible? Let us know in the comments below. We raid every one. Thank you for watching.